some point something microscopic will appear, such as the interaction between particles, the Hamiltonians, also in the quantum version of statistical mechanics, we will see density matrices and so on and so forth. So first of all, introduce, let's say, the microscopic the microphysics. This is the one of the scope of statistical mechanics. Secondly, it allows also to study states which are a little bit out of equilibrium by using, so to treat somehow the fluctuations around the equilibrium by using transport properties and or derived quantities. Or at the end also ultimately can also describe non-equilibrium systems, although about non-equilibrium system we will not say too much. Probably next week we will analyze the Boltzmann equation, which is under certain number of hypotheses, an equation which describes how system reaches at some point the equilibrium. Okay. So of course now the link between thermodynamics and microphysics sai che devo prendere un verde, questo qua fa schifo. Which is this link. Well, the link is basically the Boltzmann definition of entropy that you probably have seen already. So it's the famous equation S, where S is the entropy that we saw until now in thermodynamics. This is the Boltzmann constant time the log of omega, where omega represents basically the number of microstates which means if you describe the system in terms of Hamiltonian, microstates a microstate is determined, for instance, by the position and the momentum of particles. If you are in quantum mechanical situation, you can also have other quantities that need to be specified, so the quantum numbers of all the particles. So that determines a single microstate. So omega is a way to count the number of microstates corresponding to a macro state, which is what we basically we have perception of in thermodynamical equilibrium. Okay, so we know what is thermodynamical equilibrium. We have a sort of definition of that, which is a little bit not very precise definition, because the thermodynamical equilibrium, as I told you last time, depends on the time scales you are watching the system. So thermodynamical equilibrium means that within a, let's say, certain amount of time, you see that the state variables are stationary. Okay. So what I was saying is that we know what is that, and we know that to some extent the macroscopic system or many particle systems have some features which depends on the microphysics. Okay, although this the way to to reduce the system microscopic system to the interaction between the components is not very trivial, and in most of the cases is not even possible from the, let's say, computational point of view. It's too complicated. Okay. And now, so we know what, so we have more or less defined what is this, and this is basically a sort of postulate of Boltzmann, that these two quantities, this is thermodynamics here, apart from the constant, and this is microphysics, if you want. It's the number for the number of microstates corresponding to the same thermodynamical equilibrium state. Okay, I should specify that this is for a system in which we have fixed energy, fixed volume, and fixed number of particles. Okay, so it's an isolated system. What is basically will be the term we will use is the term of the microcanonical ensemble, okay? But we will introduce it later. Now, this is somehow a postulate which obeys to some necessary features that one has to require to the entropy, such as being an extensive variable, or well, basically that is the most important. But now let's try to see how to justify a posteriori this equation, okay, and this postulate. So the thing we will do now is a sort of exercise in which we have a system of many particles, non-interacting particles, and localized, which could have a magnetization, or could be in a couple of energy states. I will describe the situation in a moment. What we will try to do is, out of this system, is to provide a way to count the number of microstates and then to compute the entropy by using this formula. So suppose that we have n particles. This is the number of particles which are non-interacting among each other. And they are localized. Localized means that they occupy a certain position in space, like a lattice. So we will not deal with kinetic energy or potential energy. Well, actually, just potential energy, if you want. And suppose that these non-interacting localized particles, we are in one dimension, and they occupy a sort of line here. Now, I can imagine that these particles have two energy states, epsilon1 and epsilon2, or the example I will do it here, have a magnetization M, which could be plus or minus. Okay, so they could be like up, up, down, down, up, etc. Okay, so they are like dipoles, if you want. If you have an external field, external magnetic field, in presence of H, of course, there will be an energy associated with the interaction between the dipole and the magnetic field that will be, say, a piece of Hamiltonian, or a potential, if you want, that is minus m scalar H. And so this provides, well, the standard interaction between a dipole and a magnetic field, for which you have a minus here if the magnetic field and the dipole are parallel, and you have a plus. So you decrease the energy if the dipoles are aligned with respect to the magnetic field, whereas the potential energy is higher, is the highest, when they are antiparallel with respect to the magnetic field. Okay. Now, we will actually consider a situation later on in which this system, which is basically the Ising model, where actually the Ising model we will see later. In the Ising model, we will introduce also the interaction between particles and an external magnetic field. But here we are going to do something which is more trivial, but nevertheless interesting. So, like, consider the case H equal to 0. So there is no magnetic field. In presence of magnetic field, you expect that basically, and in absence of interaction, you expect that the particles will align their magnetization in order to be parallel to the magnetic field, right? In absence of interaction. Now, suppose that the magnetic field is 0, and we ask ourselves, is there any reason to expect that the total magnetization, so if you want the sum over the m, is different from 0? Well, basically, no. This is also provided by intuition. So, in principle, without a magnetic field, there is no preferred direction. And therefore, if you want the total magnetization, we expect to be 0. Let's call it m, should go to 0. So there is no reason to expect that all these spins, if you want, are aligned. They could have a plus or minus without any preference on the two sides. Okay. So this is something we can conclude easily from our intuition, but the thing is that now to compute the probability of having this configuration with total magnetization equal to 0, and to see how much or how this probability decrease once you introduce the possibility of changing the orientation of the spin or the magnetization of those particles. Okay, and in this respect, statistical mechanics is going a little bit beyond the thermodynamics. Okay, from a thermodynamical point of view, we know that the total magnetization will be 0, basically. But for that, we cannot say nothing more. But now we will see that we'll make this exercise of counting the number of microstates, and this will allow also to find or to realize how much probable is to have this configuration, and how unlikely instead is the situation in which, for instance, a good fraction of those magnets is in the same direction. This will be very, very unlikely. So the exercise proceeds as follows. Suppose that we have n plus small n divided by 2 number of particles with m plus, so up, let's say, and n minus n divided by 2 is the number of particles with n equal to minus. Okay, now what is n small n is basically the imbalance between plus and minus. Now this is normalized in such a way that the sum of the plus and the plus so the number of plus and the number of minus is equal to n, which is the total number of particles. So n small n represents sort of imbalance, so which means the number of plus minus the number of minus. Okay. So then we expect, for what we said before, we expect that n is basically is 0, or it must be very, very close to 0. It should be a very small number in any case. Okay. Now, what we will try to do is compute Wn, which is the probability of having number of, well, of having an imbalance between plus and minus, which is n. Okay, so we will try to compute the probability of having a certain configuration in which we have the imbalance n, which means n plus small n divided by 2 number of plus and this number here of minus. Okay, so we have to do this counting, and for that we have to ask ourselves which is this probability. Okay. Now, if you have n particles, the number of permutations is n factorial, no? And so here we are playing this game basically. We have a plus, minus, minus, plus, plus, minus, etc. Okay. So the number of ways to pick up n plus n half plus from n particles is, I'm going to write it now and then we will comment it. What I'm going to write is the number of ways to pick up n small n plus capital N divided by 2 plus from n particles. And this number, let me see if I get the name of that. No. So it's just n factorial, which is the number of permutations of n particles. So this is the number of ways to rearrange, no, if you want, the position of those particles, divided by n plus small n 2 factorial. And here I have a normalization, which is nothing but n minus small n divided by 2 factorial. Okay, that's sort of binomial distribution. Okay, so how many ways I can pick up this number out of the number that I have in the numerator is just the binomial coefficient. No? okay? Which is, if you want, is the number of permutations of n divided by the number of permutations of n plus n divided by 2, and the number of permutation of the plus and the number of permutation of the minus. Is it okay with that? Is it clear? Yeah. So now this is a number of ways to select this number of plus out of a total number n of particles. Now, which is the probability that we call W of n? To compute the probability, I have first of all to realize how many possible rearrangements I can have out of this n system, n particles, which could have two possible values of magnetization, which is plus and minus. And then take this number here and divide by the total number of configurations. Okay. So first of all, the total number of configurations, which, if you want, is the total number of microstates. Which is this number? Well, consider that for the first particle, I have two possibilities. So this could be plus, or this could be minus. Then for the second particle, I have two possibilities. For the third particle, three possibilities, two possibilities, etc., up to the n particle. So this takes two values. This takes two values, these two values, and so on and so forth. So then it's 2 to the power of n, the total number of states. Okay. So this is equal to 2 to the power of n. Okay. So now I can write the W of n, which is now the probability of having this number of plus, and we get the following result. So it's 1 divided by 2 to the power of n, which is the total number of microstates, total number of configuration, if you want. And here I have these binomial coefficients. Okay. Now let me. So as you have seen here, I'm doing what the Boltzmann equation is telling me, so to count the number of states and do this kind of game. So basically in statistical mechanics, we have to do this, well, this was simple, but in general it could be a very complicated combinatorial calculation, okay? In this case was simple, but in general it's not easy, and is very difficult in the cases in which you have many constraints to be fulfilled, as we will see in the following. Now, okay, of course, this is a complicated structure to be analyzed as a function of small n, and we will try now to massage this probability in order to find something which is let's say, easier to understand. And actually what we are going to obtain basically is a result due to the central limit theorem. So we will get in a moment, after let's say, a little bit of calculations, that this distribution, so this probability actually behaves like a Gaussian, okay, due to the central limit theorem, if you want, okay? So now the calculation proceeds as follows. Remember that we have derived an approximation, which was the Stirling approximation, that tells me that the logarithm of n factorial is n log n minus n, where n is a large number. So then what I'm going to do here is to apply the log in here, so the log of w, and use as much as possible the Stirling approximation. And we will see that this actually provides me a simple law for Wn, which will be a Gaussian. And once we have a Gaussian, we know that the Gaussian is determined by two parameters, which is the central value, that will be 0 as we expect, and the sigma, so the standard deviation. Okay, and we will connect the standard deviation actually to the number of particles, as we will see in a moment. Okay, so now the calculation proceeds as follows. I have to apply basically this the Stirling approximation to this expression here. So first of all, I have a minus n log 2 when I do the log of this term here. Then I have a plus n log n minus n, which is the log of the numerator. Then I have a minus n plus n half log of n plus n half plus n plus n divided by 2. And let me see if I got, yeah, okay. Then I have similarly minus n minus n divided by 2 log of the same quantity plus n minus n divided by 2. And I think I have all the terms at this level now. Now we can remove some term, which is this minus n. Then I have an n half here, and then I have an n half here. Okay, that's it. This can be written now as n log of n divided by 2, sum of this and this. Then we have a minus n plus n divided by 2. And let me collect here n half there. Facciamolo così. Log of n divided by 2. And here you have 1 plus small n divided by n. N mezzi, sì, più n mezzi, ok, questo è corretto. Yeah, of course, also these will cancel. Huh? So these are n half and this n half, this is also removed. And I have minus n minus n divided by 2 log of n half. And here I have 1 minus n divided by n. Okay, let me check if I have all the terms, just one moment. N logaritmo di n mezzi, quello lì, n mezzi, ok. Okay. Let's do this additional simplification. So I write this like in that way. then I have minus here, and here I have a log of n divided by 2 plus the log of 1 plus n divided by n. Okay, well, and similarly for the other term, which is n minus n, 2, we have a log of n alpha, log of n alpha, and I have a plus the log of 1 minus n. I think we have this correctly. Meno n mezzi logaritmo. Okay. Now let's use this approximation, this additional approximation. We expect small n to be much smaller than n, and therefore we expect this number here to be very small. It's provided by our intuition, or if you are our empirical experience. Therefore, I can use the following expansion, that the logarithm of 1 plus minus x, this is equal to plus minus x minus x squared divided by 2. A second order. And unfortunately, I have to keep the second order here. So now what we are going to do is to use this log, this expression for the log, this asymptotic expansion, in here and here. Okay. So let's try to do it. This is a calculation that one has to do. Well, it's not very difficult, but one has to do it once, and then for instance, it will be the same, basically the same for the random walk. Okay, so then we will not repeat it. Okay, so this, let's continue. This n log of n alpha minus n plus n divided by 2. And here I have a log of n half. And here I can use this n divided by n minus n squared divided by 2 n squared. Okay, and similarly for the others. So I have a minus n minus n divided by 2, and here we have a log of n half minus this time n divided by n minus n squared divided by 2 n. Okay. Vediamo se ho tutti i termini. Logaritmo, bla bla bla. Okay. Now, okay, the calculation proceeds. And I'll leave you the exercise if you want to try to do it. So you will see that, for instance, this n log of n half is removed because I have a minus n half log of n half, And here I have a minus n half times log of half, so this will this term will cancel. Also, the linear terms in small n will go away, and what will be left? Well, I can also neglect. So let me write it here. Neglect the cubic term because it's a small number. And I have a cubic term here once I have n times n squared, and also here n squared. Okay, so once you do this calculation, just a little bit of algebra, you will see that only the quadratic term in n will survive, and actually you see that this is minus n squared divided by 2n. Okay. Okay, so a term like this one, since I have an n here, and then I have an n squared divided by 2n. But you can try to do the calculation, you will see this the case. Yes. Therefore, now this was is proportional, better to say that this is proportional to our W of n. Why proportional? Because I'm using the Stirling approximation up to a certain order. So then I see that the Wn is a normalization constant, K is a normalization, and an exponential, which is e to the minus n squared divided by 2n, okay, which is a Gaussian. Why I get a Gaussian is the central limit theorem. I have the sum of many random processes, and then the sum of those will provide the distribution of all of them will be a Gaussian. No, it's the fact that the binomial tends toward a Gaussian for the limit of a large number of particles. Now I can choose the normalization K in such a way to be normalized. So then if you normalize Wn by considering that n is a number larger than 0 and compare with a Gaussian, you will see that the right normalization is the following. La scrivo qua sotto. Wn is 2 divided by pi n, and here I have e the minus n squared divided by 2n. Okay, so this is the final probability of having an unbalance, which is n. Okay? This constant here is a normalization constant. There is a factor of 2 that I have to rearrange with respect to the Gaussian. The Gaussian is, let me write it here, from minus infinity to plus infinity as the following normalization. No? The Gaussian is 1 divided by sigma square root of 2 pi. And here I have e to the minus x squared divided by 2 sigma squared. That is the Gaussian distribution. X belongs to minus infinity plus infinity interval. So here we have to normalize for positive number of n, and therefore we have a factor of 2 that needs to be considered. So it's the opposite of this divided by 2, and therefore I have 1 over square root of pi, square root of 2, which go to the numerator once you normalize. Okay, you can work it out. Now, so from this, let us discuss a little bit this formula here. Se lasciamo la gaussiana, lasciamola. So what we see here is, of course, the average value of this Gaussian, the mean of this Gaussian is n equal to 0, no? So this W1n is a Gaussian distribution with a mean which is n equal to 0, as expected, in the sense that the imbalance is 0, which means that the most probable value, which is also the mean in the case of the Gaussian, is the one corresponding to the configuration in which I have the same number of up of plus, sorry, and minus, which is of course expected. We started from this as actually we say it's very likely that there is no way to have a, let's say, we do not have a preferred direction, so then we expect to have the same number of up, of plus and minus. But the interesting thing now is that we get the sigma of this Gaussian. So from our calculations, now we have also a way to compute the sigma of this Gaussian distribution. We expected n to be the mean to be equal to 0. We didn't know which is the shape of the distribution, and now we realize that it is a Gaussian, and we also get the sigma. The sigma is the square root of n, by comparing this formula here and the formula for the Gaussian. Okay, so this is the standard deviation, which is square root of n, which means that what is called the fractional width of the distribution, maybe so the fractional width of the distribution is sigma divided by n. Why n? Because small n, distribution is in small n as independent variable, and the small n can vary in the range 0, n. Okay, so the total range of the small n is from 0 to n, and we can find a fractional width of the distribution as the total range, as the ratio between the sigma of the Gaussian and the total range of variation of n. And you see that this scales as 1 divided by square root of n. This is a very important result, because that tells you this is going to 0 when n is going to infinity, which is the case of macroscopic system. N is 10 to the 23, no, the Avogadro number. And then you see that the fractional width of this distribution actually is very, very narrow. How much narrow? 1 of square root of n, where n is a big number. It's 10 to the 23. Okay, so that means that the configuration in which small n is equal to 0, so no imbalance between plus and minus, is really overwhelming. It's just that once you move a little bit out of this configuration, the probability is very, very small. How small? Well, I mean, it's easy to find it, no? So let's rearrange a little bit probability. Okay, this was a normalization by n, and then I have an exponential of minus n squared, which can be written as follows. Minus n, then there was a 2. Let me divide it by n, make it squared, and here you have n. So I'm writing just the same thing of before. Here you have an n squared, which simplify with this, okay? So from this is more clear what's going on. If I put here, if n is equal to n, capital N, which means that, well, basically all the particles have plus as a magnetization. You see that the W of n is equal to, apart from the normalization, which is not needed in this case, is e to the minus n divided by 2. Okay? Where n is of the order of 10 to the 23. So it's something that we cannot even catch with our intuition. This number is really ridiculously small. So, to have a spontaneous, in such a system, to have a spontaneous magnetization, it's really the probability of this event, it's really ridiculously small, because here you have to substitute an exponential of minus 10 to the 23. And of course, okay, these are very, if you want, this is the worst scenario that I can imagine. But in any case, if n is, let's say, n divided, I don't know, by even 10 order of magnitudes, it doesn't change too much, okay? Because I just need to have, I will have here, instead of 20 to the 23, I will have 10 to 13, which is again a very small number, okay? Again, very small. So that means that in such a system, which is a macroscopic system, the most probable state, which is also the minimum because it is a Gaussian, is really the one that is realized. There is no way to change too much the situation. So I can have fluctuations, but those fluctuations are very, very small. For sure, to have a number of magnets with plus of the order of n is really impossible. I need to wait many ages of the universe in order to have such a situation. Okay. So this is basically, if you want, with this small exercise, so we conclude that the most probable configuration which is the one with small n equal to 0, is overwhelming, is dominant. And even small deviations are strongly suppressed. Okay? If I change n by sigma, the sigma in this case is square root of n, doesn't change too much, so it's again very small. Okay? The order of the suppression that I need to remember is 1 over square root of n, where n is 10 to the 23. Okay, this is the fractional weight of the distribution. Okay. So basically, if you want, this though it's a very simple example, it's at the core of statistical mechanics and the success of thermodynamics. So once we have reached the thermodynamical equilibrium, in this case, the thermodynamical equilibrium corresponds to the n equals 0 case. Well, this situation is as a probability which is dominant with respect to any deviation. Okay, so I can have fluctuation, of course, but those fluctuations are very unlikely to happen. Okay. Now we will realize soon that the most probable configuration is actually so if I compute, if I use the formula of Boltzmann for the entropy, we realize soon that the most probable configuration occupy a number of states which is basically equal to the total number of states. Okay, you will see in a moment what I mean. So the situation is the following. Suppose that I take n equals to 0, and I ask myself how many ways to have n equal to 0. Well, I have to use the formula of before, and I get this omega, which is the omega corresponding to the max. So number of states corresponding to the configuration with the maximal probability. Which is, of course, we said is n equal to 0. Okay. Which is this omega max. Omega max is n factorial divided by n half factorial times n half factorial. Okay. Just using the previous formula. Now, sono qua. Let's try to see what the Boltzmann entropy is telling us about the system. So let's try to compute the log of Megamax. This calculation is all the same as before. So I use again the Stirling approximation. Minus twice n log of n r plus twice. So I can remove this, and here I get this, of course, then the log of omega max is just n that I can collect, and here I have a log of n divided by 2, which is log of 2. And this is the log omega max. So the log of the total number of configuration corresponding to the most probable value is n log 2. Okay. But this is also equal, apart from a kb, is just the log of the total number of states. So remember that the entropy for Boltzmann was S equal to kb, the log of omega, where omega is the total number of states compatible with the thermodynamical equilibrium. So omega was 2 to the power of n in this case. Okay. So therefore, I get that this provides, again, the entropy is, apart from the kb, which is not important in this case, is kbn log of 2. So basically, you see that what Boltzmann is telling you with this formula is that you count the total number of states, which is in this case is 2 to the power of n, or you count the total number of states occupied by the most probable configuration. Those two numbers are the same in the large n limit. Let me write it because this is a very important thing. So let's say the number of total number of configurations. Total configurations which enter in the Boltzmann entropy is basically the total number of configuration corresponding to the most probable the total number of ways, say, corresponding to the most probable configuration, which is n equal to 0. Okay? So this is a good lesson because we will use in a moment. That is telling me, okay, this is the entropy of Boltzmann, where apart from kb, this is the log of the total number of states available for the system, total number of microstates available for the system in a certain thermodynamical equilibrium condition. The calculation that we have done is basically telling us that instead of taking omega, we can just consider the most probable configuration. Or if you want, once we have a way to compute omega, we can maximize the omega and just consider the log of the number of ways associated with the maximum of omega. Okay? Because in the large n limit, so in the limit of a large number of particles, basically the overwhelming configuration from the point of view of probability is the most probable one, of course, but it's really overwhelming in the sense that once you move from this most probable configuration, the probability to have a fluctuation is very small. Okay? So this is more or less the lesson. Let me see if I need to tell you something more about that. Okay, now I think it's basically it. Okay. And maybe we stop for a couple of minutes or 3 minutes, and then we continue. Facciamo questo esempietto qua.
prossima. Sì, però vedo che c'è una copia testa. Anche io mi stavo scordando i ringraziamenti. Così, fase definitiva, faccio bene ringraziamenti. No, non è necessario.
No, che ho inviato al prof sempre i ringraziamenti, ma l'ho stampata cosa.
Ma io non l'ho stampata con i ringraziamenti.
Grazie, non so per avermi fatto
Okay, so let's do a little bit of just one formula of math. So we are going now to generalize the situation, to do a sort of small exercise from two possible states available for each particle to total number of states, which is k. Okay, so instead of having now two states, which was a plus minus, we have k possible states for particle available for a particle, which could be, for instance, the energy levels, if you're thinking about atomic configurations, or could be, I don't know, a spin, a larger spin, spin 1, spin 2, spin 3, and so on and so forth. Okay, so suppose in general that we have k possible states available for each particle. Let me write a formula which could be useful. So, which is a multinomial formula, which is the following: is power of n. This is a math formula, which is a generalization of the binomial formula. So if you have to do the n power of this sum of variables, then this is the sum of the multinomial coefficient, which I will tell you in a moment what this, but actually it's just this, okay, factorial, x1 to the power of n1, x k to the power of nk. And the sum is done from n1 to nk, which is the number of particles in state 1 up to the number of particles in state k, under the constraints that n1 plus n2 plus nk is equal to n. So this is a constraint. So let me repeat, I have n boxes. Which are the, if you want, the n particles, and each one of these boxes can have a certain number of states, which is k. Or you can think about occupation number. You have n possible, let's say n1, n2, n3 in energy level 1 and energy level 2, energy level 3. It's not important. So the important thing now is the math. Okay. So, and out of these, we get that if you put x1 equal to x2 equal to xk 1, then here I have that k to the power of n is the sum of n factorial divided by n1 factorial nk factorial, sum of n1 and k with the constraints that n1 plus n2 plus nk is equal to n. This is a formula that we need because it's just telling you that the total number of states k to the power of n, which is of course the total number of states, as before it was 2 to the power of n, because you have 2 possible states, and now you have k possible states, and so then the total number of configurations k to the power of n is the sum of this multinomial coefficient over n1 and k, with all the possible configuration consistent with the constraint that the sum is equal to n. Okay? So these are just math. And maybe more clear. This is the total number of configuration. Once you select a certain set of n1, n2, and nk, you can compute the total number in which you can get these n1, n2, and k configurations with the multinomial coefficient, and then you sum over all the possibility consistent with the constraint that the total number of particles is n. Okay? And then you get this formula. Now, in the case that we were considering before, we were basically maximizing, well, we were basically considering the term in this sum, which is the dominant term, and we said the most probable one, and we said this is actually equal to kn. Okay? But in general, k to the power of n is this complicated sum, you know, with those constraints. Okay, so let us introduce what is called Shannon entropy. It's a sort of exercise if you want. And try to see try to apply what we have derived before, that counting the number of possible states and doing the log of this, or making the log of the number of states corresponding to the most probable configuration is actually the same. Okay, this is what we learned before. So let's try now to do it. So let us consider a certain configurations of n1, n2, and k with the constraints that the sum from I to 1 to k of ni is equal to n. Okay. So, for instance, suppose that we have 3 states, okay? And you want to take n factorial. How many ways you have to, from n factorial, to get n1 particles is n factorials with n1 particles in state 1 times the complementary, no? Which is n minus n1 factorial. Okay. And of course, now in how many ways you can arrange the left, which is n2 and n3, out of this is n minus n1 factorial divided by n2 factorial times n minus n1 minus n2 factorial. And then now we have to arrange the third, and so the n3, and you get this one, 3 factorial. And here you have n minus n1 minus n2. This will remove this, and this will remove this. That's why you get n factorial divided by n1 factorial, and 2 factorial, and 3 factorial, with the constraints that n1 plus n2 plus n3 is equal to n. Okay. So this is just to justify the formula that we wrote before, the multinomial formula for 3 possible states. No, you take an arrangement of n1 particles. In how many ways you can do it is n factorial divided by n1 factorial, and you have to normalize. Now, how many particles you have left after this? You have n2 and n2 plus n3. Now, out of these configurations, which is will be n2 plus n3, in how many ways you can pick up n2? Well, is the number of particles that are left divided by n2 factorial times the normalization. Okay. Now, how many particles are left? Is n minus n1 minus n2, and so to see how many ways you can pick up 3 particles out of these, you again divide this by n3 factorial, and then there is a normalization. In this case, that is 1. Okay. I don't know if it was more or less clear. It's a generalization of the binomial coefficient to the case of k possible states. Okay, so now suppose that you have a certain configuration with n1 and nk particles in state 1 and state k. Of course, with the constraint again that n1 plus nk is equal to n. And let's define a quantity that we call again entropy, but actually this is called the Shannon entropy or Gibbs entropy. Or Shannon entropy. And let's define these to be, let's take KB equal to 1. So we actually, it's a formula very similar to the formula of Boltzmann, but this is done in information theory. So KB is equal to 1, like this. This defined as just the log of n factorial divided by n1 factorial times nk factorial. Okay. So suppose that I have k possible states. I put n1 particles in state 1, n2 in state 2, and k particles in the state k. Then I compute the log of the total number of ways to arrange n1 particles in 1 and nk particles to state k. Okay, as we did before. Before we had just 2 states, now we have k possible states. This is the total number of ways to have this configuration. Now we can derive a formula which is actually the most common way to write the Shannon entropy by again considering the Stirling formula. Let's just do the log of this quantity. So let's expand this log. So S will be the log of n factorial, which is n log n minus n, as usual. And then I have minus the sum from 1 to k of ni log ni. I will write it down and then I will comment it. Plus the sum of from I to k of ni. Okay, so I'm just applying the Stirling formula to this. The log of n factorial becomes n log n minus n. The log of the denominator is the product. The log of the product becomes the sum of the log. Okay, and therefore I have, and then I apply again the Stirling formula, and then I get minus the sum from 1 to k of ni log ni plus sum from I to 1, so from 1 to k of ni. Okay. Now this is equal actually to n by using the constraint, and therefore this can be removed. And let me see what we can do else. There is a way to introduce a probability. So this can be written as n I log of n I. Okay, the sum over I to k of n I times the log of n minus the sum of I to k of n I log of n I. So this can be written as, so here instead of n, I'm putting the sum in order to have everything the same sum. And now I can write this as a sum over 1 to k of minus ni log of ni divided by n. Minus ni log of ni divided by n. I'm collecting this ni, then I have a log of ni divided by log of n with a minus. Okay, and let's call pi, which is a probability now. This can be interpreted as a probability, the ratio between ni and capital N. So now this is equal to minus sum from 1 to k of ni log of pi. Let me divide this by n, multiply by n, and then we get S, which is the Gibbs of Shannon entropy, is minus n sum from 1 to k of pi log of pi. This is called Shannon entropy. Well, it's another way. Well, actually, this is the way to write it usually, but can be obtained from the counting that we have done before. It's called Shannon entropy. And this is associated, it's not the thermodynamical entropy, it's something that you define for a certain specific configuration of Ni, just consistent with the constraint that the sum must be equal to capital N. Now this formula will appear in another form also in the Boltzmann equation. Okay, so it's a formula that somehow is telling you always the same thing. Means entropy, or in information theory, is basically the amount of information contained in a message, for instance. Okay. So now we will do the following game, or the following exercise. This thing is associated with a specific configuration of N1 and K consistent with the constraint is not the sum of over all the possible configurations, just one. Now let us consider the configuration which maximize the entropy, the Shannon entropy. So let us compute the configuration N1 and K which maximize the Gibbs of Shannon entropy. So to do that, now you have to maximize this formula, but by using a constraint that the total number of particles is n. So it's a typical situation in which I have to use the method of Lagrange multipliers. Okay. So this means to maximize S with respect to an I, or if you want, with respect to Pi, which is the same, under the constraint that the total number of particles is n, or if you want, the constraint that the sum of the probability is 1, which is the same. Okay? And so to do that, we need to consider minus n sum over I pi log of pi plus, here we take the Lagrange multiplier, and then we take the constraint. The constraint is that the sum over ni, or the sum, or let me write it this way for the moment, 1k minus n, which can be also written in the following way. Let me collect an n here, then this is 1, and this is pi. That I do the trick of using the blackboard. Okay. So now what we have to do, derive with respect to pi and equals equal to 0, the derivative. Now this is the procedure. We have to maximize the function plus the Lagrange multiplier times the constraint, and derives the values of pi. Of course, this will be a function of lambda, and then from the normalization we get the lambda. Okay, so now it's a matter of calculation. It's a small exercise. So when I derive, well, I can neglect n, of course, because I have to put this equal to 0, so then I can remove the n. So when doing the derivative, I get a minus log of pi, then I get minus 1 plus lambda is equal to 0, right? Minus log of pi minus 1 plus lambda equal to 0. From which I get that lambda minus 1 is equal to log of pi, from which I get that pi is exponential of lambda minus 1. Exponential of lambda minus 1. Okay. Now you have to impose the constraint. So you have to impose that the sum I1 to k of pi is equal to 1, which means that the sum I to k, 1 to k of e to the lambda minus 1 is equal to 1. Okay, which means that k times e lambda minus 1 is equal to 1. And for I need to find lambda out of this. So e to the lambda minus 1 is 1 over k. Then I take the log of this. Well, actually, this is not needed because at the end. Okay, let's do it. Actually, it was okay. In any case, so e to the minus lambda 1 over k. So I take the log of this. So lambda minus 1 is equal to the log of 1 minus 1 over k, and therefore at the end lambda is equal to 1 minus the log of k. Okay. So then is just to remind you what was the technique of Lagrange multipliers. And you take the function plus lambda times the constraint, you derive with respect to the independent variables, put to 0, find the solution, then use the constraint to derive the value of the Lagrange multiplier, which is lambda in this case. Okay? This was the procedure. Yes?
The index of summation transfers on the lambda.
What? Here?
Yes.
This is a constant. You can take this out of the sum and then it's just k. So it's a sum of 1 from 1 to k of a constant. Okay, this is lambda, and then now we can see that pi, what was pi? It was here. Well, actually, maybe this calculation was much easier. In any case, just to underline the procedure. Now lambda minus 1 is just, you see from here, that lambda minus 1 is minus the log of k, and exponential to minus the log of k is 1 over k. Okay? So pi is 1 over k. So that means that the configuration which has the maximal probability to occur is the configuration in which pi is just 1 over k, which means also that all the states have the same probability. And this is the situation of maximal entropy. Okay? Which can be also turned into the following. If you have n particles, you just distribute equally those n particles into the k states. Okay? In the sense that probability, this was actually pi was ni divided by n, and this is equal to 1 over k. That means that ni is n divided by k. So you just distribute your particles equally in those boxes or in those states with a probability which is 1 over k. Okay. Which is also intuitive in the sense that the maximal, if you want, entropy is related to disorder, no? So it's the situation in which there is no preferred states, and then you just occupy as much as possible your phase space, your available phase space. Let me see what I have done here. Now, if I compute, as we did before, now the entropy associated with the configuration with maximal probability now this S is equal to, let us remember that this was minus n, then I had a pi log of pi. But now I get that this is equal to minus n, the sum, 1 to k of pi. What is pi? Is 1 over k. And then we have a log 1 over k. Which is equal to, now this is again a constant. I can take it out from the sum. The k and the k here are removed, and this is just a minus n log of 1 of k, which is equal to n log of k. Which can be written also as log of k to the number of n, which is this number, the total number of configuration. Okay, so we get again the same result as before. This is generalized for k possible states, but the procedure, so the physics or the concept is the same basically. Okay, you can compute the entropy associated with the thermodynamical equilibrium, although here we are not talking about a thermodynamical system. Well, you can compute this entropy in both ways. Is the log of the total number of configurations as the entropy of Boltzmann, or is the log of the configuration with the maximal probability of being realized? Okay, it's the same as before. In the previous case, the maximal so the configuration with the maximal probability was small n equal to 0, which means no preferred direction. In this situation, the configuration with the maximal probability is the one in which all the boxes are occupied with the same number of particles, or if you want, all the states have the same probability of being occupied. Okay. In both cases, you get the same result. So if you want, now to some extent we are going beyond the thermodynamical equilibrium. If you want, the thermodynamical equilibrium case is the maximal entropy, Shannon entropy. Which corresponds to pi 1 over k. Okay. Whereas in general, the entropy, as it was given by this formula, which is the minimal entropy. In which case we get the minimal entropy. The maximal is all the pi is equal to 1 over k, which is in thermodynamics will be the thermodynamic equilibrium state. The minimal value of the entropy that you can have is the one in which a j, you have a pj equal to 1 and pi equal to 0 for I with respect to j. Which is the case in which just one of these pi is 1, and then all the rest are 0, which means that all the particles are in the same states, basically, in the same state, basically. Okay? What is the entropy? In this case, the Shannon entropy in this case is S equal to 0. So somehow this formula of Shannon, that will be, well, we will find something similar in the Boltzmann equation that we will see next time. Somehow allows you to treat a situation in which you have a thermodynamical equilibrium, which is this case here, the configuration corresponding to the most probable, the arrangement of pi corresponding to the most probable configuration, which is the thermodynamical equilibrium or analog. But you can also have situations, for instance, like this, in which the entropy is 0, which is this one, and you can have all the intermediate cases in which the pi are not 1 and 0, or are not constant, but they can change. Okay, which is the situation for which, and now I think I will stop on this. For instance, when considering the alphabet information theory, so each letter in the alphabet has a sort of probability to occur in a word, no? So, for instance, the A and J, at least in Italian, they have very different probabilities to occur, and then you can compute for each letter the pi and compute the entropy. Suppose that you have a word made of k letters, okay, cane. So this we have n letters and k possible states, with k is the number of the letters of the alphabet. Okay? Now you can associate with each of these letter a probability, which is the probability in that specific language to occur, and you can compute the entropy. Okay. Now, in general, so in Italian, I don't know, the probability 1 of letter A is a certain number. The probability blah blah of Z, sorry, is another number, and you can compute the entropy associated with a word or a message. And somehow, the larger the entropy, well, okay, let us consider the case, and then I will really stop. If in the alphabet only one letter would have a probability 1 and all the others probability 0, of course the entropy will be 0, but that also means that the amount of information that you provide once you send a message is 0, because the people you are talking with, they know already this distribution, the probability distribution, so they do not get any information out of this message. On the other hand, if pi are all the same, 1 over k, 1 over 21, in that case, you have a maximal entropy, which means also maximal amount of information for a message, because somehow you are breaking the degeneracy. Okay, so this entropy of Shannon is actually, which is very similar to the thermodynamical entropy, is very much used in information theory to somehow count the information, the amount of information that you have once you send a message. Okay, I think I will stop here because it's already 11 and Pappalardo is coming. Ok, ci vediamo. See you.
Arrivederci.